If you've been following along so far, you've seen me slowly working my way through Dr. Physics A's YouTube lecture, Einstein Field Equations for Beginners. My progress has essentially been based on the idea of asking what's equation 1, what's equation 2, etc. This has served me well so far. But as for equation 6, I'm afraid I may look rather silly here, but I couldn't find it. I really only watched through the video twice. I may have just missed it twice, but perhaps he never said what equation it was. So instead of looking at equation 6, I'm going to look at something I'll call equation 1b, which is right here. This is equation 1 down here. This is equation 1b. And I think perhaps more accurately it could be called equation 1 twice. So equation 1 twice has a vector equal to a Jacobian times a path element. Equation 1 has just a differential change. This is a differential vector. This is just a differential scalar. And it is the sum of a gradient times a path element. So this is the similarity between them. Here we have a vector, here we have a scalar, here we have a Jacobian, here we have a gradient. Now I'm going to introduce a little bit of extra notation to this, so we can compare these more readily. My additional notation is the introduction of these little arrows. Instead of m, I have m down. Instead of r, I have r to the right. Instead of m, I have m down. And instead of r, I have r to the right, or r down. The little arrows are a suggestion of how to implement the matrix multiplication. So here, having m down means this goes 1, 2, this goes 1, 2. Here, having r going to the right, this makes y go 1, 2, 1, 2 to the right. This having r down means having those go 1 and 2. You might notice at this point having both the arrows and the indices m, r, and s. Wait, where's the s? Oh, there's no s yet. M and r. I really no longer need to write or even think about the letters m and r. But if you are either familiar with Einstein notation or matrices, and this version provides a nice translation that could be understood either way. If you like Einstein notation, you could just ignore the arrows. And if you hate Einstein notation, like I do, then you could ignore the indices. So what is equation 1 twice? So what is equation 1 twice? Let's see if we can recall the motivating principles behind equation 1. We had kind of a hilly terrain, and that hilly terrain is in 2 dimensions. Let's see, I'll draw it like that, so I don't know. Since I can't draw, but I do have access to some good software, let's try to describe this situation with the software. Here we see a plot of pressure versus temperature, and at each pressure and temperature there's an associated volume. So even though this particular example has nothing to do with space-time, the mathematics can be similar. We could treat it as though P was the direction east, T was the direction north, and V was the altitude. Let's see if I can actually turn this so that that looks more like the reality. Okay, so looking down at it, okay, now it's more familiar, the direction of the map with P going east and T going north. Nope, I've still got it goofed up because this goes 50,000, 100,000, 150,000. Let's try that again. Turn it up this way, spin it all the way around, and then bring it this way and see if we get it. Okay, now we have P going upwards to the right, and so that can be our east. And T going upwards. Ugh. Alright, let's try one more thing. Maybe this time going up, going right. Thank God. I am also not a master of the Rubik's Cube. But anyway, now this goes upward to the right as a standard graph does, and this one goes upward. Really? Oh, I forgot to copy and paste it. Let's copy it and paste it. Okay, now this goes to the east, 50,000, 100,000, 150,000, 200,000, and this goes north, 100, 200, 300, 400. Okay, finally I have the coordinate system so that this goes positive, this goes positive, this goes positive. And I can get back to what I was actually planning to talk about, which was essentially, and I think I need to do something so I can see, or just turn it around so it's facing me. Let me draw kind of this line right here. The slope of that line represents the change in volume per change in temperature at those points along the curve. So there could be a higher change in volume per temperature, like up here. That is a steeper slope than this one. And maybe down here it's a slightly less steep slope. Now if I turn that around like this, then you can see, let's see, I'll draw that. You can see the del V, del P slopes coming along here. The slopes of those particular lines are the slopes of, or the change in volume per change in pressure. Now if you want to know, say from here to here, what is the change in volume in that tiny little section there, that change in volume is going to be equal to the change del V del P times the change in pressure plus del V del the other part, del V del T times the change in temperature. So you basically go a little bit this way, or the slope of that way times the change in that direction, plus the slope in that direction, plus the change in that direction. Now that only works for a little differential element here. It's that you can see even here that the slope in the dVdP changes quite a bit right there as you are moving up. So it only works in that little tiny section, but it works in that little area. And the way that that's described by equation 1 would be del V del P comma T, whoops, P comma T times, well, let's say del V del P comma T to the right, then times D Yeah, dp comma t going down, which would be del v, del v del p, del v del t, matrix multiplied by dp dt. Now, in Einstein notation, well, in the equation that we'd be doing right there, del phi del pressure and temperature, what do you want to call that? Del y, and then del y sub, I don't know, r, and dy sup r. We'll just call where y is p and t. Y is equal to the set p, t. So that's essentially equation 1. Now what equation 2 does is it basically says that instead of having instead of having a single value, V, at each of these pressures and temperatures, we're going to have two different values. For instance, the example that I've been giving up to this point, so the example we have been using is x equals r cosine theta and y equals r sine theta, or their inverse, r equals square root of x squared plus y squared, and theta equals arctangent of y over x, plus pi if x is less than 0. So essentially we can think of this as two scalar fields. Here they are. The figure on the left is the field associated with r equals square root of x squared plus y squared. That should seem pretty natural. The height variable is proportional to the distance from the center, so you get a cone. The figure on the right is what you would get associated with theta equals arctangent y over x plus pi if x is less than 0. This, as you can see, has a spiral staircase feel to it, ascending as you go around the origin counterclockwise. And then jumping back down again, jumping down to the bottom, and then climbing back up because the angle goes from negative pi to positive pi. Of course, if I change the variable to degrees by multiplying times 180 divided by pi, then it would start at minus 180 degrees and go up to positive 180 degrees up here. And that is at x equals negative 2. So generally the x and y variables would be held that way, with x going to the right and y going up. And we would usually start the staircase here at 0 and go up to 180 and then continue up all the way up to 360. So this gives a number, this particular function gives a number between negative 180 and 180. But there's another way to write it so that it goes from 0 to 360 degrees. Okay, so one more time I'm going to go through equation 1, d phi. I just replace that phi with r, and which is del r del x, del r del y, and then times the differential path element dx dy. Can do the same thing with d theta, which would be d del theta del x, del theta del y, and our differential path element dx dy. Okay, so equation 1b is equation 1 twice, where where we just go dr d theta equals del r del x del r del y, I'm going to have to move over a little bit, times dx dy, but then I don't have to rewrite the entire thing, I just have to rewrite this part of it, del theta del x and del theta del y. So there it is. Equation 1b is equation 1 twice. There's one other thing that I should mention in case you need to write this equation in the other direction horizontally. Then the matrix multiplication will be the transpose of each of those and reversed, dx dy times, and then you can write the other part of it here, except it's got to be the transpose, del r del x del theta del x del r del y and del theta del y. I think in the previous video we established that the outer product of two vectors could be useful for several reasons. Reminder, an outer product of two vectors is the vertical form a sub x, a sub y times the horizontal form b sub x, b sub y, and you end up with a sub x, b sub x, a sub x, b sub y, a sub y, b sub x, and a sub y, b sub y. So that is one reason that I have written this dr d theta in its horizontal form. It may be helpful to have it in both its vertical form and its horizontal form in order to do an outer product or an inner product, anything related to this differential path element in an alternative coordinate system. Anyway, I will go into more detail on. So coming up next, I expect to go into more detail on the use of the outer product of the differential path element. That's the replacing this with dr d theta and dr d theta. Go into more detail on the use of the outer product of the differential path element, and I will see if I can make any sense out of something they call the metric tensor.